Hello, this is section 2.4, day 2, and we're going to continue discussing the chain rule. And there's some really important rules in this second part of the lesson, and many of them you're just going to have to memorize. So the nice thing is, you'll notice in this first box, you know all of these. We're just saying if there's something other than just x in the angle position, then you'll have to multiply by the derivative of the inside. So the key thing is all of the ones that we did previously to this second day, it was just the power rule that was always on the outside. Now we're going to talk about how the outside function isn't going to be always as obvious, and especially with trig functions, it can get a little bit tricky. So, but in this case, we treat the sine part or the trig part as the outside. So notice that's what you do the derivative of, where the inside stays the same, then times the derivative of the outside, or the inside, excuse me. So you multiply by the derivative of the inside. So, but you'll notice from there, sine, tangent, secant squared, secant, secant tangent. Notice here, when you go to rewrite this, the derivative of the outside, it's secant of u times tangent of u. And then you multiply by the derivative of the inside only once. I'll catch students trying to multiply it twice, but you just multiply, always go back to your original and multiply by the derivative of the inside, okay? So that's what these problems are. So here's a really basic one, and you'll notice it's not just x, it's 3x squared. So you do the derivative of the outside, so sine turns into cosine, where the inside stays the same, times the derivative of the inside. And there it is. Same thing here. It's just a binomial that's on the inside. Now here's where things get more interesting. So sine squared, that's what this is. So I would highly suggest you rewrite it as sine of x all squared, because then you can easily see it. But be careful how you write that notation. You don't want to just put the squared here, because then you might think it's x squared. But now you can see where it's actually a chain rule problem. And you start with the outermost part, so, and that's the squared on this case. So pull that 2 down, inside stays the same, times the derivative of the inside. And this derivative is a basic derivative, but you're done. Now, with this problem, again, rewrite this. So cosine of 4x squared, all squared. And then you can see, oh wow, this is actually a double chain rule problem. You have the squared on the outside, and then here inside, cosine is the outside of this part, the 4x squared. So you have a double chain rule problem. So start with the outermost function. So deal with the 2 first. Pull that 2 down in front. All of this stays the same. Now turn your attention to doing this derivative. Oh, and don't forget to subtract 1 from the exponent. Now turn your attention here. So now you do the derivative of the outside of this, which is the cosine. So it's negative sine of 4x squared, then times the derivative of the inside, which is 8x. You can see where that can get a little complicated. So you'll need to practice these. All right, and then here's some more practice. So if you haven't learned by now, if ever there's a fraction with a variable in the denominator, if you have a number in the numerator, just move the denominator up and make sure you make the exponent negative. Okay. But this is a straightforward product rule. So first times derivative of the second, tangent turns into secant squared of 1 over x, or x to the negative 1, times the derivative of the inside. That's where you're using the chain rule. Plus second times derivative of the first. And then just clean it up. Try to get rid of negative exponents. We don't typically leave negative exponents. And then this one's very similar to D. Rewrite it as tangent of 4x all cubed if you need to, and go from there. Good one to practice. All right, but just be careful. Trig functions can be a little bit tricky, all right? Sometimes, yeah, so you just need to practice these. Okay, the next big one is natural log, and this is one that you'll have to memorize. And I did the proof over here for you. So I started with just y equals natural log of x, did base e both sides to rewrite it. And then I went ahead and did this derivative, and I used our new concept of the chain rule, where e to the y, remember e, the derivative is the same thing, so I left it e to the y. But we have a function here, y, So I multiplied by the derivative of that, wrote it as dy dx. You could have also written y prime equals, and then of course the derivative of x is 1. Well, if we solve this, dy dx, so divide over the e to the y. But remember, back at the beginning, y equals natural log of x. So I replaced the y with natural log of x. And then, of course, that cancels. And look, dy dx equals 1 over x. So it's a nice little proof. We used a concept called implicit differentiation that you haven't learned yet, but that's coming. And of course, you would never have to do this proof on your own. It's just fun to see how we get to our derivative. But for you, you need to know dy dx means you do the derivative. And derivative of natural log of x is 1 over x. And that's, of course, when x is greater than 0. Natural log has a restricted domain, and already this argument here has to be greater than 0. All right, so when you see natural log of x and I ask for the derivative, immediately in your brain you need to think 1 over x. Just like when I ask for the derivative of e to the x, you need to immediately know that's e to the x. Or sine of x, the derivative is cosine of x. So a lot of these you just need to have that readily available in your brain. And if you're not doing your homework, if you're doing your homework, it's going to come very easily to you. But you have to be consistent with your homework. All right, now, and then here's this chain rule. So if you have something other than x, we have to multiply by the derivative of the inside. Okay, and then with absolute values, already you have positive numbers because of the restricted domain. So notice you get the exact same derivative. So let's look at some of these. Now for this one, I actually did it 2 different ways. I expanded it. And remember, natural log of 2 is just a number, so the derivative is 0. And then this becomes 3 times 1 over x. So that's one way to do it, or treat it how it is. Natural log, the derivative sends the inside, or the argument, to the denominator. That's what I did first, but then I have to multiply by the derivative of the inside. So that's where this 6x squared is coming from. And if you simplify, look what you get. 3 over x. It's the same thing. Hey. Okay. So this next one, product rule. That's pretty straightforward. Just make sure you simplify these x's. Now with C and this letter A over here, these two problems look very similar, but you do them completely different. So in this case, are you allowed to move the 2 in front? No, because it's not the binomial squared. Whereas in this case, yes, you are. It's the arguments, the binomial that's being squared. So you are, in fact, allowed to move the 2 out in front. Okay. But going back to this one's a chain rule. It's actually a double chain rule. So pull the 2 down in front, inside stays the same. Subtract 1 from your exponent. Now focus on this derivative, and it's another chain rule. So natural log sends this argument to the denominator. That's the derivative. That's how you do the derivative of natural log. But then times the derivative of the inside, which is just 1. Now this one, since we were able to move 2 in front, it becomes, this is just a scalar now, so it just stays out in front. Natural log, that derivative sends this to the denominator. And the derivative of the inside is just 1. Now, do you remember back in Algebra 2 when we used to make you expand? You had to practice expanding and condensing your natural log problems. And you said, what is the point of this? Well, here you go. Look at this problem. Oh my goodness. If you tried to do this derivative as it's written right now, whew, you'd have to do quotient rule. Well, first, natural log would send this entire thing to the denominator. Then you'd have to do quotient rule combined with product rule and chain rule. I mean, it's doable, but that's not the path I would suggest you go down. Instead, take advantage of those expanding properties. You can, anything in the numerator, break up and add, and then anything from the denominator becomes a subtraction, and you can move those exponents out in front. And look, you have a whole new expression that's the same. But look at each individual derivative. They're so much easier. Okay, and then I did have, in class, we'll focus on this, getting a common denominator, combining, like, just a refresher on your skills there. Because eventually in the next chapter, we're going to take these and set them equal to 0. And it's much nicer to have this to set equal to 0. Look, I know exactly where my derivative's undefined, where I might have an asymptote or a sharp turn, as opposed to this does not give me a whole lot of information. Okay. All right, the next big ones. So definition of exponential function to base A. So this is just a couple properties just to refresh your memory. How you could rewrite these. This was your change of base and some other important things. E to the natural log of x is x. Natural log of e to the x is x. Don't forget you can also rewrite the bases. So, but here's the important thing. Here's the calculus. So d dx of a to the x. Now, when you do this derivative, it's natural log of the base times the original exponential. Now, this is the same as e to the x. But if this was e to the x, it'd be natural log of e times e to the x. Well, what's natural log of e? It's just 1, so we don't write it. So you've been doing this all along. This is the new component because it's not base e, it's base a. Now, when you do log base a of x, same thing. It's 1 over natural log of the base, which is a, times x, which that's the same with natural log of x. It would have been 1 over natural log of e, which is 1, times x. So these, nothing new. It's just when the base isn't e, you have to have this extra natural log of the base in there. So I know this looks intimidating, but it's really, you've been doing another thing you've been doing all along. We just don't write it. Okay. So here are some of those practice. So 6 to the x, do not use the power rule. You cannot pull x down in front and subtract 1 from the exponent. This is not a power rule problem. So you have to do natural log of the base times the original exponential. Done. Same thing here. Natural log of the base times the original exponential, but in this case it's something other than just x, so you have to multiply by that derivative, which is 3. And that's the chain rule part. That was over here. Okay, so log of sine of x. All right, so here we go. Log, that's going to be 1 over natural log of 10 times 1 over the inside. Up here it was just x, but when it's something other than x, you notice it's u down in the denominator, and then times the derivative of the inside. You'll need to practice these. These are a little weird at first. Now here's another one where we expanded before we did the derivative. Okay, so, oh, sorry about that. Don't know what happened there when I scanned this in. So this is just some refresher on some algebra concepts. So you guys can look through that. And I guess if you have any questions on this stuff, email me. All right. And some of you are really good. Some of you maybe struggled. So, and you might be playing a little bit of catch up. And if you need me to sit down with you and thoroughly go through any of these problems or any of the properties that you don't remember, or the expanding, condensing stuff, just shoot me an email. We'll set up a time to Zoom or meet in class. Okay. But guys, you have to practice these derivatives. Please, please, please do your homework. And definitely email me if you have any questions. Okay.